Alright, so I want to just kind of look at linear independence again from the same example we did before, but look at it in the definition of linear independence. So again, basically we're starting with three functions, and all we do is we construct an abstract linear combination of these functions. So c1 y1 plus c2 y2 plus c3 y3, where c1, c2, and c3 are just constants. We don't know what they are yet. And we set that equal to 0. And we say what restrictions must be put on those numbers c1, c2, and c3 to make that true. If the restriction is extremely high and the only way that can happen is to make all of those numbers 0, then the functions are linearly independent of each other. If not, then they're dependent. So once we plug in and imagine this linear combination, we go ahead and distribute the constants. And we c1 times x plus 1, I have to distribute that. So it's going to be a c1x plus c1, and so on. And then all we do is we look at that linear combination, we distribute all the constants, and then we regroup terms into the like terms. These are all power functions, so we have an x squared term. So when we simplify this expression up here, it's going to be c2 plus 2c3 times x squared. And then when we simplify it and put all the x terms together, it's going to be c1 minus c3x. And then when we put all the constant terms together, we get c1 minus c3. And that has to be equal to our y1 function, I'm sorry, it has to be equal to the 0 function. But since this is a quadratic, all that means is 0x squared plus 0x plus 0. So again, the point of these equations is that we're not solving for x. X is a variable, and this equation has to be true for all values of x. So we can just match up the x squared terms. So the c2 plus 2c3 has to be 0 because there's 0x squared. The c1 minus c3 has to be 0 because there's no x, and the c1 minus c3 has to be 0. So again, from the previous example, we saw that really two equations were telling us the same thing. The same thing's happening here. We really have two equations and two unknowns. And if we solve that system of equations, which is really easy to do, there's actually many solutions because there's only two equations and three unknowns, so there's actually going to be infinitely many solutions. You can basically choose any value you want for one of these numbers, and then these two equations will tell you what the other two numbers have to be. So I just happen to choose 7 for C1, and once I do that, it forces me to choose 7 for C3, and then it forces me to choose negative 14 for C2. The point is, we constructed a linear combination of our three functions, and by choosing non-zero coefficients, we can actually turn that linear combination into the 0 function, which means those functions are dependent on each other. It means just what we saw in the last video. Any one of those functions we could write as a linear combination of the others, so they depend on them. So these are linearly dependent functions. In general, polynomial functions like this is really the only ones you really have to check, because it's not obvious by looking at them always. But many other examples, it is pretty much just obvious. Let's look at these four functions I have up here. They're all similar in nature, but they're all different. If we just look at these carefully, and again, you can read these notes to see kind of why I'm explaining to you why these four functions are linearly independent. If we created an abstract linear combination of these functions, none of these functions are like terms. They would never combine into one of the other terms. Like, there's no way you can possibly, just by looking at these, there's no way that any one of these functions you could possibly write as a sum of three terms involving the other three functions, because they all have fundamentally different factors. First one and the second one, look, they're the same except one has an x, one has an x squared. Well, we already know that x and x squared are independent. So these are independent. But any group of these, there's no way. You have to think about a linear independence as the ability to simplify a linear combination into a different linear combination of less terms. But the problem is you have to keep the linear combination in terms of the functions you have in front of you. So again, there's no way I can write any one of these functions as a linear combination of the other three. There's really nothing to prove here. It's just kind of look at it and think about it. But that's what linear independence is. And we're not going to really need to know how to test this all the time anyways, but it is an important concept to kind of have in your mind. But if you don't understand it completely, or how to confirm it in every conceivable example, just ask. Sometimes any particular example is going to be just a little bit weird, and there might be something odd about it that makes it non-standard. But generally the idea is, if you can write any of the functions as a linear combination of the others, then they're dependent. So it's easier to somehow prove their linear dependence than it is independence in many cases. But oftentimes independence is almost obvious by looking at the functions, like in this case.